The fold illusion, the origins and implications of ogives on silicic lavas. Folds on the surfaces of mafic lavas are among the most readily recognized geological structures and are used as first-order criteria for identifying ancient lavas on Earth and other planetary bodies. Ogives, sometimes referred to as pressure ridges, are parabolic, laterally discontinuous ridges and troughs occurring on the upper surfaces of many lavas, varying in composition from basalt to rhyolite, and they are characteristic of silicic lavas. We prefer the non-genetic term ogives to pressure ridges. The patterns produced by ogives are remarkably regular and predictable, suggesting that their sizes and spacings relate to the mechanical nature of the lava and the deformation processes operating during emplacement. Figure A here is a side-on view of a large ogive ridge and trough pair in fine vesicular pumice of Medicine Lake dacite lava at Medicine Lake Volcano, California. The tallest surface you can see there is about 5 meters high. Now, ogives do not include recumbent folds at the margins or the interiors of flows, nor the abundant and topologically diverse centimeter to meter scale folds found within lavas. So, for example, none of the other 3 photos are ogives. B is a large recumbent fold in the center of a rhyolite lava at Burrow Creek, Arizona. C is a 10 centimeter scale overturned intrafolial fold in Big Glass Mountain at Medicine Lake Volcano. And D is a crease structure. So ogives often occur with and are often cross-cut or truncated by crease structures. These are 10 meter to meter scale splaying fractures. That one's in the Medicine Lake dacite. So several studies have applied aspects of fold theory to ogives in attempts to constrain silicic lava viscosity during flow. Studies based on fold theory attribute the frequencies and amplitudes of folds to viscosity contrasts between adjacent layers. Folding of the upper surface implies that rheology is predominantly ductile and the stress state is primarily layer parallel compression. This has implications for the thermal structures of silicic lavas and the timescales of their emplacement. Here we re-examine this paradigm using field and laboratory investigations and find that the behavior is predominantly brittle and the stress regime is extensional. We interpret ogives to be fracture-bound structures, more like crevasses in glaciers than folds. For example, if compressional folding produces ogives, they should be best displayed where lava has flowed against an obstacle. This is Obsidian Dome in California. Here we see well-developed ogives in the northeast, southeast, and southwest quadrants, where the lava flows unimpeded downwards into drainages. But there is a notable lack of ogives in the northwest quadrant, where lava ponded against higher topography. There we get rectilinear fractures. Here's a hybrid digital terrain and elevation model of the interlake lava at Newberry Volcano in Oregon. Ogives are well developed along the flow axes, but weak, shown by white arrows, where the lava impinged against the central pumice cone, which was a topographic barrier. In B, zooming into the east lobe of the interlake lava, we see that ogives fail to form continuous smooth parabolas and are instead formed by acute intersections, marked by the yellow arrows, between 50 to 100 meter long straight fractures. C shows a side-on view of a prominent ogive ridge on the Medicine Lake lava, showing the ubiquitously fractured upper surface, and 2 sets of orthogonal clefts forming seracs. Those parallel to the ogive ridge are shown in orange, and those cross-cutting the ridge are shown in yellow. Ogive ridges are straight 10 to 25 meter long sections that narrow from 5 to 20 meter wide at the base to acute fins at the crest. The upward-facing surfaces of ogive ridges are pervasively fractured by rectilinear and polygonal sets of millimeter to 5 centimeter wide, less than 50 centimeter deep, tensile fractures, where each fracture tapers into the rock. The ridge margins are usually curviplanar surfaces of fine vesicular pumice or obsidian, but infrequently obsidian is covered by 2 distinct veneers. These are, shown in 6A, polygonal fractured and stretched red-brown oxidation surfaces, and in B, convoluted oxidation surfaces where alternating flow bands protrude in and out of the plane of the fracture. Some of the polygonal surface shown in A, that material can be traced down into welded and non-welded lapilli tuff-filled fractures, as shown in C. Locally, we find a third veneer type of polygonal fractured and stretched, about 1 millimeter thick, pink or lilac tuffisite on either fine vesicular pumice or obsidian, and that's shown in 6D. These are clasts that have been plastered onto the side and also stretched. Many indisputable centimetre to metre scale folds are exposed within ogive ridges and on their flanking surfaces. However, none have been found that form the ridge itself. Fold attitudes range from upright to recumbent, shown in B and A, and all are closed to isoclinal, similar style, disharmonic intrafolial folds with gently curvilinear hinges. Many of the largest folds refold smaller folds around their hinges, for example in C. When crease structures and clefts are restored, many of the upright isoclines become recumbent and the flow banding subhorizontal. So, consider restoration of cartoon outcrop A, which is typical of many of our field observations. Interpreting the ridges as upright buckle-style antiforms and the trough as a synform, in B1, requires that the folds be restored by stretching the upper surface. Doing so rotates the flow banding to subvertical and does not allow marker bands on either side of the trough to match, shown in B2. The marker bands can only be matched together by a second, otherwise unknown phase of folding prior to erosion to make the subhorizontal surface. Interpretation of A as a tensile fracture like a crease structure, shown in C1, requires restoration simply by closing the fracture. The marker bands then match, as shown in C2. We prefer that one. So, we also measured the rheology of pernicious rhyolites from obsidian dome using parallel plate viscometry. The Arrhenian diagram, shown in A, shows that fine vesicular pumice has a higher viscosity than dense obsidian with a similar water content, then that's due to the bubbles. On the right, the Deborah number is calculated for a deformation time scale, think of it as an emplacement time scale of 0.1 years, demonstrating in this case that pernicious rhyolites should behave brittly below about 640 degrees C for coarse vesicular pumice, or below about 680 degrees C for fine vesicular pumice. We modelled cooling timescales of obsidian flows, considering radiative and convective cooling from the surface and conductive cooling through the base of the flow. Calculated cooling rates agree with experimentally determined cooling rates of silicic lavas from Lipari, reported by Gottsman and Dingwell, 2001, which ranged from 0.013 to 4.2 Kelvin per minute through the glass transition. Therefore, cooling at a rate of about 0.2 Kelvin per minute from an emplacement temperature of about 800 degrees to the brittle ductile transition temperature, which we just established was about 680 degrees for fine vesicular pumice in the upper crust of the lava, this would require about 10 hours. Using the lower temperature for the brittle ductile transition, which could occur as low as about 614 degrees for an avesicular obsidian containing about 0.28% water, that would require about 16 hours. However, the surface layers of most rhyolite lavas are fine vesicular pumice, so we prefer the more rapid estimate. Note that we assumed low values for the convective cooling coefficient of about 10 watts per meter squared per Kelvin, low value of crust temperature, about 323 Kelvin, and eruption temperature, 1065 Kelvin, which results in a conservative estimate for cooling rates at the surface of the flow. If we assume very efficient convective cooling, a hot crust, and a higher emplacement temperature, the timescale over which the upper surface remains ductile and capable of folding will be only about 100 minutes. So in summary, brittle temperatures are achieved in less than a day. There would be less than 24 hours available for folding to occur to form ogives if they were formed by folding. Our conclusion, based on field evidence, rheology, and stress modelling that I didn't have time to get into, is that ogives are tensile fracture-bound ridges and not folds. Silicic lavas are gravity spreading, with the upper surfaces deformed brittly and mostly in extension. Fold theory has been applied widely to ogives to constrain the rheology and composition of inaccessible lavas, for example submarine and extraterrestrial lavas, and has received renewed interest for terrestrial lavas due to the increasing availability of high-resolution digital terrain models. Understanding how silicic lavas are emplaced is changed fundamentally if ogives are not folds, and the application of fold theory is not valid. So our conclusion is that the presence of ogives on the surfaces of lavas on other planetary bodies may help to elucidate their rheological properties and crustal thicknesses, but relating to their tensile strength, not their viscosity. Thanks very much for your time.